Hi everyone, I'm Xing. On behalf of my teammate Melody Borg, we will present how we built and validated our learn default classifier, how we improve macro F1 score on an imbalanced dataset, and how we ensure the model generalized reliably. Our final solution is a tune like GBM and XGBoost off assemble, evaluated with stratified cross-validation and optimized using a data-driven probability threshold. This is a binary classification problem predicting Lorentz status, where defaults are the minority class. Because the dataset is imbalanced, accuracy can be misleading. A model could appear strong while missing many defaulters. Therefore, we optimize macro F1 score, which balanced precision and recall across classes and better reflects the minority class performance. We engineered 3 rattle-based features to normalize financial behavior, like above. These features capture financial burdens and borrower maturity related to life stage. Rattle features allows tree-based models to better separate risk level compared to raw magnitude alone. We also convert object type columns to categorical types so that gradient boosting models could handle them effectively. We tuned light GBM using Optuna. We use a stratified 80-20 split and optimized macro F1 score on the validation set. We tuned tree depths, numbers of leaves, learning rate, sampling, and regularization parameters, and apply early stopping to prevent overfitting. This tuning process significantly improved model stability and performance over default parameters. We evaluated 3 model approaches: 1 tuned light GBM, 2 XGBoost with scale pulse weight to address imbalance, 3 a soft assemble averaging predicted probability from both models. For XGBoost, we set scale pulse weight equals to number of negatives divided by number of positives. The assembles perform best because averaging probability reduces variance and improves generalization. We handled imbalance using class weight equals to balanced in light GBM, scale pulse weight in XGBoost. This increased the penalty for misclassifying the defaulter and improved minority recall. Instead of using the default open fight cutoff, we optimize the probability threshold using the precision recall curve. We compute the macro F1 across all thresholds and select the one that maximizes the performance. The optimal threshold was 0.6212. Using this threshold, our out-of-fold macro F1 reached 0.9024, demonstrating strong balanced performance across classes. This showed that aligning the decision rule with the evaluation metric significantly improved practical results. To ensure robustness, we use 5-fold stratified cross-validation. Stratification prevents class proportion in each hold. For each hold, both models were trained and out-of-hold probability were collected and averaged. The final out-of-fold macro F1 of 0.9024 reflects stable performance across partition, not just one favorable split. We generate a learning curve using the tuned light GBM model and macro F1 score. We train the model on increasing proportion of the data and compare the training and cross-validation performance. The curve coverage at a high level of limited gap, indicating strong generalization and no serve overfitting. This visual diagnosis confirms that model capacity is well calibrated to the database set. We plotted a confusion matrix using the optimized threshold. In a lending context, false negatives present approving risky borrowers lending to financial loss. False positives represents rejecting safe borrowers leading to opportunity cost. By optimizing macro F1 and selecting a threshold of 0.6212, we balance these trade-offs rather than relying on arbitrary 0.5 cutoff. This makes a model not only statistically strong but also aligned with financial risk management principle. The precision recall curve were used to evaluate trade-off across threshold. Rather than using it only a visualization tool, we directly compute macro F1 across threshold and select the optimal decision boundaries. This ensures our classification decisions are metric driven and data informed. If we had more time, we would incorporate macroeconomic indicators and more detailed credit history features to capture systemic risk. In production, we will monitor performance over time and detect data drift to recalibrate threshold or retain the model when borrower behavior shift. To summarize, we engineered radar-based financial features tuned like GBM and with Optuna, trained like GBM and XGBoost, combined them via straw assemble validated using five-fold stratified cross-validation, optimized the probability threshold to 0.6212 and achieve an out-of-fold macro F1 of 0.9024. The final model demonstrates strong generalization, robust validation, and meaningful business arrangement for imbalanced loan default prediction. Thank you.